Hello, in this video, we're going to cover parametric surfaces. To introduce parametric surfaces, it's helpful to recall the information that we have about parametric equations, right? So what is a parametric equation? Right, so if we go through and define x, y, or x, y, z coordinates, using functions, of a parameter t, then we would say that's a parametric equation. So if we define x, y, or x, y, z coordinates using functions of a parameter t, then that gives us a parametric equation. So examples would be x equals f of t, y equals g of t, or in 3 dimensions, we could have x equals f of t, y equals g of t, and z equals h of t. In both these cases, so these are examples of parametric equations. In both cases, you can go through and you can reformat these into vector functions. And vector functions are equivalent in terms of functionality to parametric equations. So to go through and define a parametric, to go through and define a vector function that is equivalent to the parametric equation, you take the definition for x and you multiply it by I, and you take the definition for y and you multiply it by j. So this gives us a definition for the x component and a definition for the y component. And in 3 dimensions, we have r of t equals f of ti plus g of tj plus h of tk. Right, and then once you have these parametric definitions, what you can do with them is you go through and you plug in t values, and out come either points, if you define it in terms of x, y, or x, y, z, or vectors that terminate at the points that you would have gotten from the parametric equation. So the result of a vector function, you end up getting a vector, but the vector terminates at the same place where the parametric equation definition you would have would have gotten you that point. Okay, so that's why they're functionally equivalent. In terms of going through and graphing parametric equations or vector functions, you can go through and you can plug in t values and out will come points. And if you just plot those points lie on a curve. Okay, so the result of a parametric equation is a curve. So if we just take the 3 dimensions here, and let's just say we had a curve going through space here. The idea is if we went through and plugged in t sub 1, and you could use either this definition or this definition, you'll end up getting this point here. So the shorthand, if we do r of t1, we'd end up getting this point. Now, again, this produces a vector, but the vector terminates at that point. If you plug in r, you could plug in t2, and you get r of t2. You could plug in r of t3, and you get r of t3, right? And assuming t1 is less than t2 is less than t3, right, you get this directionality to parametric equations that the curve ends up graphing over increasing t. Okay, and so that's the very basic, simplest kind of introduction to parametric equations, and it serves as a good place for us to go through and define our parametric surfaces. Okay, so the definitions are all going to be very similar, right? So watch this. Okay, so we're going to go through and say, now we're defining a parametric surface. Okay, and so what we do is we go through and we define x, y, z, right, using, let's just say x, y, z coordinates using functions of parameter U and V. Okay, and so if you look at the two definitions, you define XYZ coordinates using functions of a parameter T, define XYZ coordinates using functions of parameters U and V. So two parameters instead of one parameter is what ends up producing a parametric surface instead of a parametric equation. And so we'll talk a little bit about why that is in just a moment, but just to go through and write these out. So you could say X equals F of U comma V, Y equals G of U comma V, and Z equals H of U comma V. You can also form this into a vector function, same way that we do with T. We'll have R of U comma V, and that equals F of U comma V I plus G of U comma V J plus H of U comma V K. Okay, so in terms of going through, and so that's the very basics. In terms of going through and sketching a graph, similar to what we did with the parametric equations, okay, you can go through and you could plot points in a similar fashion to what we did with our parametric equations. So we ended up using plotted points and ends up producing a curve. However, the difference, of course, is that we now have two variables that we're going to end up plotting points for. And if you go through and just vary one of the two variables, then when you're varying one of the two variables, it's going to end up behaving the same way that the parametric equation does, where you go through and vary the only variable. All right, so like this. So let's go through and say that we had a surface. Let's go through and try and sketch something that looks like a surface. All right, so let's say that's our surface, and it's kind of a bent over. If you took a plane and you just kind of bent it, that you'd get this portion of a plane that's just kind of bent. The idea is if we pick some spot on here. Okay, so let's say that that spot is R of U2 comma V2. That just kind of gives us a starting point. Okay, and again, I'm using the vector function format, but technically you get a vector that terminates there. That's going to be our format for going through and representing points. If you go through and you just vary U2 and you keep V2 constant, right, then by keeping V2 constant, if the only thing that's changing is U2, then in that case, it's going to behave like a parametric equation, right? If there's no V variable, if you're not changing it, the only thing that's changing is just one variable. Well, one variable changing produces a curve. And so what we're going to get by doing that is we're going to get a curve that's on the surface. So you could go through and say, for example, let's say this is R of U1 comma V2, and here we get R of U3 comma V2, and those lie along a curve. We can go through and maybe use a different color, right? So you end up getting a, missed. You end up getting a curve that sits on the surface. A little bit hard to draw, but now if we go through and you vary V2 instead of U2, right? So V and U presumably are defined differently in the function. So you're going to get a different curve. Okay, so if we go through and say plug in, maybe this point over here, we could plug in R, that's R of U2, because we're keeping U2 constant, and that's R of U2 V1. And then maybe we get over here, we get R of U2 comma V3. Then you'd end up getting a different curve that's on the surface when you go through and vary V instead of U. And so if you're sitting at this point here where R of U2 comma V2 is, the fact that you've got two different variables and you could vary each one, meaning you get two different directions. Well, two different directions, if you were thinking about it, two different directions, that's going to define a surface, not a curve. Okay, and so if you just think about being here and you could walk this way or this way, by definition, if you've got two directions is what's going to define a surface, all right, not a curve. And of course, you could combine these by varying u2 and v, by varying u and v, and end up getting, curves that go like this, or like this, or like this. And before long, you've got your idea of a surface. So the two variables here is the key piece to what ends up making a surface instead of a curve. And so that's why, that's how we go through and define parametric surfaces, is using two variables. Okay, so what are we going to do with these parametric surfaces? Well, of course, we have gone through, throughout this course, we've gone through and we've used a lot of different surfaces. We've used rectangular coordinate surfaces, we've had cylindrical coordinate surfaces, we've had spherical coordinate surfaces. And so this section is going to try and tie at least some of those into parametric surfaces, like make a connection between the two. All right, so what we're going to do first in terms of that connection is we're first going to look to translate from a parametric surface into a rectangular coordinate system. All right, so let's look at translating from parametric surface to rectangular coordinates. All right. So let's look at an example, and then I'll explain how to do this through the example. All right. So suppose we have a parametric surface, and again, we're using our vector function format for defining it. And so that equals cosine of u I plus sine of u j plus vk. So the question is, what is this surface in rectangular coordinates? And so how can we go through and translate that? Well, the method that you use is going to be the same method that you use to translate from a parametric equation into rectangular coordinates, into xy or xyz coordinates, depending upon the function. And then the goal is going to be to eliminate the parameter, or parameters in this case. All right, and in terms of going through and doing that, again, hearkening back to our parametric equations, anytime we see sines and cosines together, immediately we're attracted to the idea of using the identity, sine squared plus cosine squared equals 1. So we have sine squared u plus cosine squared u equals 1. And then, I've skipped a step there. What you first need to do before you do that is you need to go through and translate this into actual parametric equations. So you want to go through and do x equals cosine u, y equals sine u, and z equals v. Right, so it's the same thing with parametric equations. I just skipped that step. Once you've done that, then you can go through and recognize, oh, hey, I got sines and cosines together. Let's use the identity. And then you're going to take those variables and pop them into your identity. So we're going to get sine u is equal to y. So sine squared would be y squared. Cosine is equal to x. So cosine squared is going to be x squared equals 1. So what does this tell us? Without doing any additional work, right? It tells us that the relationship between x and y for all of the points on the curve is going to be 1, right? If there were going to be something different, then you would have had you'd have another variable present in the problem, and we'll do an example like that where you can see how the relationship between x and y actually changes. But in this case, the relationship between x and y is constant. All right, so we have x squared plus y squared equals 1. So we know for all points that are on the surface, x squared plus y squared equals 1. So what does that sound like when you think about what type of an object that would be? If x squared plus y squared equals 1 is always equal to 1, all right, then if you were thinking in terms of trying to sketch an object that actually satisfied that kind of characteristic, you would think in terms of, all right, well, if x squared plus y squared is 1, and assuming that part of the object is at the xy plane, that's x squared plus y squared is 1. And then if I, look, if part of the object is at z equals 1 and x squared plus y squared equals 1, then I end up getting, this type of a shape. And it's like, oh, wait, that looks kind of like a cylinder, right? And so the fact that x squared plus y squared is always equal to 1, it's kind of screaming at you that's a cylinder. To go through and check whether it's a cylinder or not, the last thing that you need to do is you need to come over here and take a look at the z coordinate and see that, oh, z is in terms of the other variable, which means z is free to be anything. Okay, if that might not necessarily be the case, you could have cosine ui plus sine uj plus 1k, right? So you could have it so that there is no v, coordinate. That is allowed with functions. That you could still have r of u comma v and still have just v always be 1. And then in that case, you would not end up getting a surface. You just end up getting a curve instead of a parametric surface. You need to have both variables present to get a surface. But you do need to check and see and look at the other variable. And so the fact that the other variable is equal to v and there's no limitations on v tells us that z can be anything, right? And so if you go through and think about what type of an object you end up getting where x squared plus y squared has to be 1 and z can be anything, that is a cylinder. All right, and so that's how we could go through and translate this initial definition here into a cylinder. It's a circular cylinder. Okay, so let's go through and try another example. All right, let's say that r of u comma v equals v cosine ui plus vj plus v sine uk. All right, and so similar to the last one, we start off x equals v cosine u, y equals v, z equals v sine u. We see we got sine and cosine there, so immediately we're like, oh, yo, the identity. All right, and so in terms of sine u is going to be z over v, right? So we could just put z over v squared. Cosine is going to be x over v, so we could put x over v squared. And then if we go through and simplify this, this is, we could just change the order here and square. We're going to get x squared over v squared equals, not equals, plus z squared over v squared equals 1. And then we can move the v squared over and we get x squared plus z squared equals v squared. So this would be an example of where we do not have a constant radius, right? So in this example, we had x squared plus y squared is 1. And so we know that's true for all xy values. Meanwhile, for this case, we have x squared plus z squared equals v squared. And we know that v can change, right? There's no limitation that's placed upon v in the original problem, which means that the radius itself is going to change as well. You do not have a constant radius in this case, and this is what it would look like if you do not have a constant radius. All right, so to go through and finish this, what we've gone through and we've gotten rid of the parameter u, but we still have the parameter v, which we would like to be able to get rid of if possible. And what we can do is we can go back to our definitions here. We can see, oh wait, y is equal to v, right? So if y is equal to v and we have v squared over here, we could just go through and replace v squared with y squared, right? And we end up getting this object. Okay, now it may have been a bit since we've looked at graphing objects, three-dimensional objects, but this object is a cylinder. Or not, sorry, not a cylinder. This object is a cone. And so we've got a cone, and so you could go through and you could so we could go through and we could pick specific values here. So if you go through and you set z equal to 0, you know that part of the cone is going to have equation x squared plus x squared equals y squared. Right, so we could go through and we could graph x squared equals y squared. And also x squared equals negative y squared. Okay, and so again, where did that come from? I just set z equal to 0. So if z is 0, then you get x squared equals y squared, which is going to give you these two lines, y equals x and y equals negative x. You could also set x equal to 0, and then you'll get z squared equals y squared, which is going to give you two lines, z equals plus or minus y. And so for those two lines, want to go through and do something like this. And then, so that's going to be the positive y equals z equals y. And then we also have the negative, which is going to look, these lines are going to end up kind of a little bit on top of each other, but hold on. Like that. All right. And then in terms of going through and sketching it, what we can do is we can pick a spot here on the y-axis. So we start there. If you go up, you'll hit the curve. That's going to be a point that's on it's going to be on our surface. If you go down, you're going to hit the curve, and so that's another point. And then if you go in the x direction, you hit the negative x direction. You hit, and then so this gives us our circular cross section, right? That we had right here that was changing with v or changing with y. Okay, and you could do the same thing over here. Just pick a spot, you go up, hit the curve, go down, hit, and then here, here, and we've got another. So we end up getting a cone. Right, and so that's what this guy is. All right, so let's go through and look at a couple more examples. So those are examples where we have circles as cross sections. So not every example is going to have a circle as a cross section. You could have something like r of u comma v. This is actually a common example where you've got ui plus vj plus 2u minus 3v k. All right, and so when you get an example like this, the first step is the same. You do x equals u, y equals v, z equals 2u minus 3v. Okay, when this happens, where you've got two of the variables are just set equal, x and y or x and z, two of the variables are just set equal to u and v, to go through and form the rectangular coordinate equation, just take those two and just plug them into the other variable, into the other equation. And so if you do that, you're going to get z equals 2, and then u is x, so we get 2x, and v is y, so we get minus 3y. And that's it. So equations sometimes are parametric surfaces are sometimes defined this way, and when they are, it's very easy to go through and translate them into rectangular coordinates. Easy enough that I went through and I just wrote up another example for us to go through and look at. If you've got something like, ui plus f of u comma vj plus vk, right? This is another same example, except I just have made the function generic instead of giving you 2u minus 3v. Then it's just x equals u, y equals f of u comma v, and then z equals v. And then you just take these two and pop them in, and so you get y equals f of x comma z, and that's your equation in rectangular coordinates, is y equals f of x comma z. Okay, and so those are examples of how to shift from a parametric surface into rectangular coordinates. All right, so let's go ahead and look at translating from rectangular coordinates to parametric surface. Again, let's just go through and look at some examples. I think that's the best way to kind of figure this out. So if we start off z equals x squared y, right, and we want to go through and convert this into a parametric surface, how do we do that? Okay, so the method actually is really simple when you have a variable by itself. So in this case, we have z by itself. If you have z by itself, or x or y by itself, what you want to do is you want to take the other variables, the variables that are not by themselves, and define those in terms of u and v, and then the z equation, will, or x or y, whichever variable is by itself, that last equation you'll just substitute into to end up getting your parametric surface. So in this case, since z is by itself, we'd go through and we do x equals u, y equals v, z equals, then take these and substitute them in, and you're going to get u squared v. And then you can rewrite that as into a vector function format. R of uv equals ui plus vj plus u squared vk. This is really the reverse of the example that we just looked at. And it can be applied anytime you've got one of the three variables by itself. So it's very simple to go through and parameterize a surface that is defined, where one of the three variables is by itself. So we are going to talk about what happens if one of the variables is not by itself, but just want to make sure that is simple, right? So that is understood. So let's just go through and make up an example here. So let's say we've got x, and it's defined using, well, let's just use a generic function, f of y comma z, right? If you have x equals f of y comma z, and it doesn't even matter what function of y z is, there's some function. How would we go through and translate this into a parametric surface? How would we parameterize this? All right, the way that you do it is you go through and you say y equals u, z equals v, and then x equals f of u comma v. And then your parametric equation then, your parametric surface then is going to be r of u comma v equals f of u comma vi plus uj plus vk. Okay. And so very simple examples, if we've got one of the variables by itself, then it's really easy to go through and parameterize the surface. Now, what if you don't have a variable by itself? Okay, well, there's a few cases. We're going to break these down one at a time. So there's cases for when we don't have a variable by itself. All right, so the first case we're going to look at where we have circles for cross sections. Right, and to be more specific, it's when our equation has x squared plus y squared, or y squared plus z squared, or x squared plus z squared. So if you see any of these in the equation that we're trying to translate, then that's an example where we have circles for cross sections. So how do we go through and translate these? Let's actually pick an example. So we've got x equals y squared plus z squared. Oops, this one actually has a variable by itself. that's fine. You could make this x squared, but the example I did is with x. So I don't want to muck up the example. So yes, technically you have a variable by itself, so you could use the previous method. But let's just say that you didn't want to. We want to go through and we want to use a different method than that. Some of these objects can be parameterized in multiple ways, which is actually a good thing to know anyway. All right, but this is a good example where we do have one of these three cases. And so we have circles for cross sections, and we want to go through and parameterize our surface. How do we do it? When that happens, you want to go through and use cylindrical coordinates. All right, so what is cylindrical coordinates? We have definitions for r and theta and z. And so what we want to do is we want to use the translation formulas for so x equals r cosine theta, y equals r sine theta, x squared plus y squared equals r squared, and tangent of y over x equals theta. All right, so we want to use these cylindrical coordinates translation formulas to translate our rectangular coordinate equation into a parametric surface. All right, so how do we go through and do that? Well, what we're going to do is we're going to use these formulas, and what we're going to do is we're going to pick the things that are squared, and we're going to kind of just swap out x and y for them. So what we can do here is you could go through and say, you know what, I'm going to have y equals r cosine theta, so I'm going to replace x here with y instead, and then I'm going to have z equals r sine theta, so I'm going to replace the y here with z instead. Now if I do that, that means that y squared plus z squared equals r squared. So I can write that y squared plus z squared equals r squared. Right. All right. And so now take a look at these three equations I've got. What I've done is I've gone through and found definitions for two of the three variables. I found a definition for y and I found a definition for z. They just come built in out of the cylindrical coordinates. And so the only thing we have left to do is to figure out what x is, to go through and have our surface parameterized. Okay. And so how could we do that? Well, look up above. We've got y squared plus z squared is x. Y squared plus z squared is r squared. So you could just pop in x equals r squared. And that's it. The surface is parameterized. It's like magic. Okay. And so what you can do here, well, there's actually one last thing that I actually recommend you do, because otherwise you'll get confused later. I recommend going through and replacing these with u's and v's. I would go ahead and replace the r's with u's and the thetas with v's. Do you have to do that? No, but it's just going to make things a little bit simpler when we actually start applying calculus to our parametric surfaces. Things get confusing if you have r's and thetas in here because of their similarity to polar coordinates. You'll want to think of them in terms of polar coordinates. And you can say, well, we are using polar coordinates here, but you just got to trust me. It's easier to go through and disconnect the variables from r's and thetas when it comes to actually doing problems. You're less likely to make mistakes. And so here, what do we have for x? X is r squared. Oop, hold on, we just said we're going to replace it with u. So we're going to get u squared I, and then plus, and then I'm going to do y, and I'm replacing r with u and theta with v. So I'm going to get u cosine vj, and then for z, we've got u sine vk. Right. And so again, it's almost like magic. So let's kind of go over that again. It might seem like, like we've skipped a step or something in there. So you start off, you've got your equation, and you want to, and you recognize that you've got y squared plus z squared in there. So you go ahead and you just write out your cylindrical coordinate translation formulas. And then you're going to take the variables that are squared, the variables that are squared that are made us recognize that we've got circles for cross sections, and you're going to substitute them into these formulas. So we're going to put we put the y where the x is, and we just wrote that out. We get y equals r cosine theta. We put the z where the y is, and we get z equals r sine theta. And then at that point, we recognize, hold on here. hold on here. When we go through and we parameterize, we find an equation for x, an equation for y, an equation for z, an equation for x, equation for y, equation for z. Equation for y and z are done. And so that leaves us only one of the variables left to figure out, and that's x. And we can go through and use the definition for the surface, to end up figuring out what the definition for x is. Then once you've got all three, you can go through and just substitute u for r, v for theta, and you've got your parametric surface. It's really that simple. Okay, so love those. It's kind of cool how easy it is to go through and parameterize. Let's look at another example. All right, so for this one, we've got 9 equals x squared plus z squared. All right, so this one is a little different. It is similar to the last one in that we have that x squared plus z squared. We do have circles for cross sections, and so that means that we can apply that cylindrical coordinate method. So just go ahead and start off and just write those. We're going to have x equals r cosine theta, y equals r sine theta, x squared plus y squared equals r squared, and then tangent of y over x equals theta. All right, and so again, first step is to go through and just substitute. So we're going to take x and we're going to put it where the x is, so that one doesn't change. So we get x equals r cosine theta. And we'll take the z and put it where the y is, and so we're going to get z equals r sine theta. And then if we go through and take those and put them where the x and z is, that means we're going to have x squared plus z squared equals r squared. Okay, and now, so we've got two of the definitions for two of the variables. We've got x and z. What about the third? We need something for y. Before we can get there, though, we're trying to do that similar to the last example, but we notice, oh, wait, hold on, x squared plus y, z squared equals r squared. 9 equals x squared plus z squared. We could put 9 where the x squared plus z squared is, and you'll get 9 equals r squared. Hold on, r equals 3. Oh, whoa, whoops. So now if you take r equals 3 and you plug them into these two, we actually have x equals 3 cosine theta and z equals 3 sine theta. Right, and then we've used everything up. We've used up this, we've used up this, everything is used up. So the question is, well, what is y? All right, well, go back to the original problem here. When you go through and when you go through and think about sketching this, right? What is this? It's a cylinder. And what do we say about cylinders, right? If a variable is missing, it means that variable can be anything. So y can be anything. If y can be anything, right? What should we define y as if y can be anything? Well, if one of our variables is theta, we could just define it as the other variable. In this case, we could just say it's v. All right. And so this will end up where x and z, because of the way that we've defined them, will have this relationship where x squared plus z squared needs to be 9. And then y can just be this floating second variable that can be anything. And that's going to end up, by varying y, we can end up getting our cylinder surface. Okay. And so when we go through and translate this, well, not translate, but when we go through and write this into the vector function format, let's go ahead and replace the thetas with u's. So we're going to get 3 cosine ui. And then we've already said y is v, so we don't need to do any kind of translating there. We'll just have vj. And then for z, we've got 3 sine uk. Again, I just took the thetas and replaced them with u's when I went through and translated this over into our vector function format. Okay, and so that's how to go through and handle circles that have cross sections. And these are really the main two cases. You're either going to have a case like this, where when you go through and do the substitution, you can end up defining the third variable by using the result the way that we did here, or it's going to turn out that the third variable could be anything like we had here. It's one of those two. All right. Case 2. So case 1 was circles for cross sections. Case 2 is when you have spheres as part of the object, so spherical object. I guess the object is part of the object is a sphere. Let's put it that way. All right, in other words, you've got x squared plus y squared plus z squared is present in the problem, right? So just like here we had x squared plus y squared plus z squared, or x squared plus z squared. If part of the object is a sphere, you're going to have x squared plus y squared plus z squared. So you might be looking at it, wait, so part of the object could be a sphere and part of the object could be not a sphere. Well, the object could be a portion of a sphere, right? So you could have the object as an entirely a sphere, or it could be a hemisphere, it could be half of a sphere. All right, and so there are possibilities where you have part of the object as a sphere. All right, so suppose we wanted to go through and we have x squared plus y squared plus z squared equals 9. We're given this and we want to go through and parameterize this surface, define a parametric surface, define this parametrically, as a parametric surface. So how do we do that? Well, if you've got sphere stuff in the equation, then hopefully it makes sense. Hopefully, at least you're immediately thinking it. Well, when I had circles, I used cylindrical coordinates. When I have spheres, I should use spherical. All right. And so what are our definitions for spherical? We have x equals rho sine phi cosine theta. We have y equals rho sine phi sine theta. And then we have z equals rho cosine phi. And then finally, x squared plus y squared plus plus z squared equals rho squared. All right. All right. And so if we can start off by going through and just using these as our definitions. So we could say x equals rho sine phi cosine theta, y equals rho sine phi sine theta, and z equals rho cosine phi. You might look at this and be like, cool, I'm done. I've parameterized this surface. Well, little problem here. Okay, so, and I haven't made this quite crystal clear enough, but parametric surfaces are defined in terms of two variables. So we need to have two variables here. Each definition. So x can be defined in terms of two things, y in terms of two things, z in terms of two things. We cannot have x, y, and z defined in terms of three things. So we've got one variable too many over here. So we need to go through and get rid of one of those variables. So how can we do that? Well, we haven't used our third equation, which, in the other problems we have. So if you've got x squared plus y squared plus z squared equals rho squared, and we look at our equation and it's x squared plus y squared plus z squared equals 9, then that tells us that 9 equals rho squared, and we could rewrite this as rho equals 3. If rho equals 3, you could pop that into here and you'll end up getting x equals 3 sine phi cosine theta, y equals 3 sine phi sine theta, and z equals 3 cosine phi. And so you can see we've got x, y, and z defined in terms of two other variables. And so that gives us our definition for our parametric surface. The one thing you can do is we go through and do r of u comma v. And as I said, we're just going to go through and replace variables. And it doesn't matter which one you make u and which one you make v. Let's do u for, just to go from left to right. We'll do u for phi and v for theta. So we're going to have 3 sine u cosine vi plus 3 sine u cosine vj plus 3 cosine uk. Okay, and that's our sphere defined using parametric All right, let's look at another example. For the next two examples, what we're going to do is we're going to look at objects that have restrictions on some of the variables. So it does make for a slight variation in terms of the process that you go through, but it's very similar. So let's say that we wanted to go through and parameterize, right? So we want to find the parametric surface for the part of the cylinder x squared plus y squared equals 9 between z equals -4 and z equals 4. All right, so this is very similar to the previous problems we've done, except we don't have the entire cylinder. We only have part of the cylinder. So how can you go through and parameterize a surface when you only have a restriction on what part, you don't have the entire surface? How do you go through and do that? Well, you want to start it off the same way. So we're going to go through and we'll say, all right, we've got a circle for the cross section. So we're going to do x equals r cosine theta, y equals r sine theta, and our x squared plus y squared equals r squared. Actually, because x squared plus y squared equals 9, because we don't even need to do any swapping here. These could be our three, it's kind of our starting definition here as we just write this and this. So we do have x and y defined in terms of our third variable. Again, just like what happened earlier, though, with the cylinder case, if you take 9 and pop it in here, it turns out that you end up getting a specific definition for r. And so this is going to become x equals 3 cosine theta and y equals 3 sine theta. Okay, and so we're not going to end up substituting this in and getting our definition for z. And so we have to figure out what z is. Well, just like what happened a few minutes ago, if we go back and look at the original problem, with the cylinders, z can be anything. And so you just set z equal to the other variable. So let's say z equals v. Okay. And now, so in terms of going through and representing our surface, we have r of u comma v. Let's replace the thetas with u. So we're going to have 3 cosine u I plus 3 sine u j plus vk. All right, and now once we've gone through and parameterized it, what we can do is we can actually just look at and say, all right, well, if this is not the entire cylinder, that means that we only have a portion of it. That means we need to go through and place a restriction on our surface, because otherwise we're going to get the entire surface. So the way that it currently is written, it's the entire surface. The restriction that you need to place upon it is that z is between -4 and 4. What is z? Z is v. So v has to be between -4 and 4. So if you just do this, that's it. We've now restricted the surface so that we only have the part. And so we're still going to get the cylinder, but we're just going to get the part that's between where z is between -4 and 4. All right, so let's try an example with spheres. All right, so let's say we want to go through and find the part of the sphere. X squared plus y squared plus z squared equals 36. And we want the part that lies between z equals 0 and z equals 3√3. All right, so we want to start off. We've got x equals rho sine phi cosine theta. Y equals rho sine phi sine theta. Z equals rho cosine phi. And again, we're like, oh, well, we wanted to define these in terms of 2 variables. 3 got 1 too many, so we need to get rid of one of these variables. How could we do that? Well, we still haven't finished with all the translation formulas. There's x squared plus y squared plus z squared equals rho squared. And then at that point, we look back to our original equation. Oh, look, x squared plus y squared plus z squared equals 36. Just pop that in. We get 36 equals rho squared, or rho equals 6. And then putting that in, we get x equals 6 sine phi cosine theta. We get y equals 6 sine phi sine theta. We get z equals 6 cosine phi. We can go through and represent r of u comma v. Again, putting u's where the phi's are, v's where the thetas are. We're going to get 6 sine u cosine vi plus 6 sine u sine v j plus 6 cosine u k. So that gives me the entire sphere. Now, however, we want z to be between 0 and 3 root 3. So if we go and take a look at our three equations, we're using these three. Take a look at our three parametric equations that we've created here. Just take the one that has z in it, pop in these guys as the endpoints. So we need to have, let's see, where should we do this? Let's do it here. All right, so we're going to have 0 equals 6 cosine phi. All right, so that means that we're going to get 0 equals cosine phi. And then when does cosine equal 0? It equals 0 at pi over 2. Meanwhile, we have 3 root 3 equals 6 cosine phi. And then so divide over the 6, you're going to get root 3 over 2 equals cosine phi. And then so what angle gives us root 3 over 2? It's going to be phi equals pi over 6. Okay, and so at one point when phi is pi over 2, we're going to have 0 for the z coordinate, and when phi is pi over 6, we're going to have 3 root 3. So what we want is we want phi to be between those two. And so if you just go over here and say, all right, so phi is going to be between pi over 6 and pi over 2, and that ends up being our answer. So we get, that's for our answer. So this gives us the entire sphere, and then we went through and placed a restriction on one of the variables so that we only get the part of the sphere where we have z coordinates between 0 and 3 root 3. All right, let's look at another example here. What about the part of the ellipsoid x squared plus 2y squared plus 3z squared equals 1. We want the part that lies left of the xz plane. Okay, so in this case, we don't have x squared plus y squared. The 2 here fouls that up. We don't have x squared plus z squared or y squared plus z squared. We don't have any of those. So we don't have circles for cross sections. We have ellipses. Those are not the same. This is not a sphere. The 2 and 3 screw this up so that it's not a sphere. It's an ellipsoid. Okay, and so because of that, we cannot go through and use cylindrical coordinates or spherical coordinates, right? So instead, we need to go through and fall back on an older method, a simpler method. And so let me just show you something that maybe you haven't thought about in ages, or maybe immediately everyone's screaming it at this, while watching the video. Let's say that you have a circle. Actually, what am I doing? I have a circle tool. Let's say that you've got a circle, and that circle is defined by x squared plus y squared, let's just say equals 4, just for sake of an example. We've got 2. Right, so what we can do is we can go through and we can find parts of this circle by solving for either x or y. Right, if you want to go through and find the piece, so you can't go through and the way this is, you cannot go through and find an equation for x or y that's going to give you the entire object. The reason is that it doesn't pass the vertical line test or the horizontal line test. All right, so the vertical line test would tell us whether we could define the entire object in terms of y. It fails. So you cannot go through and define the entire object in terms of one y equation. Horizontal line test does the same thing for x. It fails. So you cannot go through and say y equals and get the entire object with one equation. You can't go through and get x equals and get the entire object with one equation. However, what we can do is we can go through and define this in terms of pieces. So if you go through and solve for y, what happens? You're going to get y squared equals 4 minus x squared. And then you're going to get y equals plus or minus the square root of 4 minus x squared. All right, so notice we've got two definitions here, right? So those two definitions gets me pieces of the circle. So the positive root here defines the top half. So if you go through and say, all right, well, the top half here is y equals positive root 4 minus x squared. And then the bottom half is y equals negative root 4 minus x squared. Okay, and then you could do something similar with x. You go through and solve for x, then the right-hand side, we could define using x equals the square root of 4 minus y squared. And then the left-hand side, you can go through and define using x equals negative square root of 4 minus y squared. Right, so this enables you to go through and cut the object into pieces depending upon what you want. Right, if you want the top half, you solve for y. You want the bottom half, you solve for y. You want the right side, you solve for x. The left side, you solve for x. So in terms of thinking about this, the vertical side, you solve for the vertical variable, right? So y is the variable that goes up, so we solve for the y if we want top or bottom. And then if we want left or right, then the variable that goes left to right is the variable that we get by itself. All right, so now going back to this problem here, since we cannot go through and use our cylindrical or spherical method, the only thing that we can fall back on is solving for one of the variables. And then the question is, which variable do we want to solve for so that we get the part of the ellipsoid that lies to the left of the xy plane. All right, so right and left, which variable is the right and left variable? Okay, that's the y variable. The y variable is the right and left variable. So we want to go through and solve for y here. If you do 2y squared equals 1 minus x squared minus 3z squared, and then y squared equals 1/2 minus 1/2 x squared minus 3/2 xz squared, and then we do y equals plus or minus the square root of 1/2 minus 1/2 x squared minus 3/2 z squared. All right, what we've done here is by solving for y, we've gotten the part of the ellipsoid that's to the right of the right side of the ellipsoid is the positive root, and the left side of the ellipsoid is the negative root. And since we're told to find the left side of the ellipsoid, we just want the negative root. All right, so we can go through and say y equals negative square root of 1/2 minus 1/2 x squared minus 3/2. So this is our object that we want to go through and parameterize. How do we parameterize it? Well, what we can do is we fall back on our definition that we had earlier, where you have one of the variables by itself. Set u and v equal to the other variables. So we can go through and say x equals u, z equals v, and then y equals negative root 1/2 minus 1/2 u squared minus 3/2 v squared. And then finally, you can represent that as a vector function. So you get r of u comma v equals ui, or I guess maybe minus, not plus here, minus the square root of 1/2 minus 1/2 u squared minus 3/2 v squared j plus vk. And so that's how you can go through and define a part of a surface when you can't use cylindrical or spherical coordinates, and you've got to fall back on our, kind of traditional method, what you want to do is just solve for one of the three variables. And hopefully the problem is going to give you something where you're either trying to find the top half or the bottom half, the right half or the left half or the front half or the back half. And then so that ends up fitting together with solving for, one of the three variables. Okay, so we're going to move on now. So that's going to cover all of our, in depth, hopefully with a lot of depth there. We ended up covering how to go through and define surfaces, how to either shift from a parametric surface to rectangular or from rectangular to parametric. Now, what are we going to do with this? Well, we're going to go through and do surface area. So we've already covered surface area. I want to be crystal clear about this. We've already covered surface area for rectangular coordinates. So now we're covering it for parametric surfaces. All right, so let's go through and just kind of go through a quick little derivation here. We've got a surface. Again, it's kind of just bent over surface. It's a parametric surface, R of u comma v. And what we're going to say here is that R of uv equals x of uvi plus y of uvj plus z of uvk. And then u of v are defined in terms of some domain. So there's some restriction on it, and that restriction ends up creating this piece of surface here that we've got. All right, and what we want to do is we want to go through and find the area of this surface. So as you may recall from the surface area video earlier that we did, what we ended up doing is we ended up chopping up the surface into a bunch of little areas. So we're still going to go through and use that method. All right, so the idea being, if you kind of pick some spot on here, if we end up varying u, you'll get a curve like this. If you end up varying v, you're going to get a curve like this, right? So that means that we could go through and chop this up into pieces. Something like this, right? And you get the idea, and we can kind of extend that. And what we want to do is just add up the area for those pieces. All right. So let's think about how we could go through and do that. So what I want to do is I'm going to grab one of these pieces. I'm just going to blow it up into a big zoomed in picture. Let's take this piece here. This looks like a good example here, right? So what we've got, what does that look like? So it looks something like, I'm going to do my best here. Something like that, right? And let's go through and pick a corner of that picture and here, and let's say that is ui comma vj. All right. So if we do that, and the sides of this object represent, reasonable steps between pieces, right? Then this piece here is going to be, we can go through and get that by varying u, right? So in that case, we would get, this is ui plus a step. We'll just use change in u. You could also use this ui plus 1, but anyway, it's simpler to go through and represent ui plus change in u. And then this is vj, where that does not change. And then this point here, we could go through and represent, this is ui, because u is held constant, but we've got vj plus change in, oops, I don't know why I put a line over it, because I was thinking it's like a vector function, but no, it's not. Vj plus change in v. Okay, now this is where we got to go back all the way to beginning of the semester, vector function stuff, right? If you took this point here, sorry, you took these coordinates here and you plugged it into R, what happens? You're going to get this vector here. If you take these coordinates and you plug it in, what's going to happen? You're going to get this vector here. If you take those two vectors, and you take those, so this one is going to be R of ui comma vj. This one's R of ui plus change in u comma vj. If you subtract those two, what happens? You get the vector that points between them. You get this vector. Okay, and so a couple things we could notice about that vector. It's kind of, I mean, it's kind of like it's sitting on the surface. It's kind of like the tangent vector. All right, it's the tangent vector in the, it looks like the tangent vector that's in the u direction. And so if that's a good observation, and it actually turns out to be true that that is what that's going to be, we're going to end up kind of creating something using that idea. And then you could go through and do the same thing with this point here. If you take that point and those coordinates and plug it in, you're going to get, oop, that's supposed to be a vector, not a line. Oops. You'll get this vector here. And then if you go through and subtract the coordinates, you'll get this vector here, which kind of it's like it's sitting on the surface. So that's kind of like a tangent vector too. All right, and that one would be by subtracting, r of this set of coordinates minus r of this set of coordinates. All right, so let's go ahead and just kind of do that and kind of clean up our picture here because it's looking a little bit like a mess. All right, so I'm just going to erase this and this and this, and then we're just going to go through and just put our definitions on these. All right, so this guy here is r of ui plus change in u comma vj minus r of ui comma vj. Kind of ran out of space there. And then this guy here, let's just do it this way, do a little arrow. That side there is going to be r of ui comma vj plus change in v minus r of ui comma vj. Now take a look at those. Look at how much those resemble our partial derivative definitions. Okay, and so what we can do here is we can inherit from our partial derivative definitions that r of ui plus change in u comma vj minus r of ui comma vj over the change in u limit as change in u goes to 0 is equal to the partial derivative of r with respect to u. Right, so this would be this format is the same format that we used for our partial derivatives. It's just applied to a vector function instead. And so you can go ahead and you can just inherit this result. Okay, and then similarly, we could go through and say that the limit as change in v goes to 0 of r of ui comma vj plus change in v minus r of ui comma vj all over change in v equals r differentiated with respect to v. Okay. Now, the thing is, we don't have this exact thing. If you look over here, right, we don't have this change in u in the bottom, and there's no limit. So what that means is we can go through and take these definitions. We can kind of just do we can do this, just erase this and say, these aren't equal, they're approximately equal. Then we can go through and we can take this, we can erase this, and erase this. We could say that they are approximately equal. And by doing that, we then can take the change in u, move it over to the other side, and you get r of ui plus change in u comma vj minus r of ui comma vj is approximately equal to r differentiated with respect to u times change in u. and R of ui comma vj plus change in v minus R of ui comma vj is approximately equal to R of v times change in v. So what we've done is we've gone through and we've found a definition that's approximately equal, but that's okay. We found a definition for this vector and this vector. How is that useful to us? Okay, well, if our goal is to find the area, we want to go through and find the area for this piece. And we've got these vectors that are on the sides of these pieces, on the sides of this piece, that roughly fit onto the piece, right? Then how could we go through and find an approximation for the area of this piece? Again, we got to go through and inherit something from very, very beginning of the semester. We said if you have vectors that define the sides of a parallelogram, then the length of the cross product of those vectors will give you the area of the parallelogram. So if we go through and do something like this, use a different color here, we could take this vector, slide it over, and we get that side. We could take this vector, slide it over, we get this side. Look at that. We've got a parallelogram. And what we want to know is we want to know the area of that parallelogram. It's going to be the length of the cross product of the two vectors that define the sides of these two vectors. All right, so it's going to be the cross product of those two vectors. So what we can do is we could say the area of the piece that we're looking at is going to be R of u change in u cross R of v change in v, and then with length, so the length of the cross product. Right, so the length of the cross product of these two vectors. This vector we're saying is approximately this, so that's why I'm using this instead of that. We're saying this vector is approximately this, so that's why I'm using this instead of that. Okay. And then from here, what we're going to do is we're going to do a little bit of just kind of cheating, hand waving, whatever you want to call that. We're going to go through and we're going to use a property of the cross product that we defined many, many moons ago to pull out the change in v and change in u. So you can actually rewrite this. This is change in u times change in v times ru cross rv. I guess it's really not hand waving. We're just inheriting more stuff from earlier in the semester. And then if you have a scalar times a vector and it's inside of a magnitude here, a property of magnitudes is we can pull out the scalar. And so this becomes ru cross rv change in u change in v. So this gets us the area of just this piece, which is one piece amongst many. To go through and get the rest, we go through and we just throw in a summation and another summation. And the second one is really ugly. I have to erase it. It's so ugly. So we can go through another summation at j equals 1 to m, limit as mn goes to infinity. And look at that. We've got our definition. This becomes a double integral, length of ru cross rv dA over d. This is our definition for the surface area for a parametric surface. Okay. And again, the d here is the same d that we had here. So that is just the restriction on UV that defines the surface. So the d is going to be the bounds that defines the surface. So it just kind of all fit together. It makes sense. All right, so let's go through and try a couple examples using this surface area definition. All right, so we want to go through and find the surface area. For the part of this surface, part of the plane. R of u comma v equals u plus v comma 2 minus 3u comma 1 plus u minus v. Oops. Like that. All right, and we're told that u goes from 0 to 2, and that v goes from -1 to 1. Okay. Now, it might be that you could find a way to do this without using the parametric surface definition, but we want to go through and practice using the parametric surface. So do not go through and turn this into X, Y, Z rectangular coordinates and then use the surface area definition from earlier in the semester. Do not do that. We want to practice using our definition that we just created. All right, so let's go through and do that. We're going to do first R differentiated with respect to U. Now, when you differentiate a vector function of two variables with respect to one of the two, you differentiate each of the components using in terms of that variable. So we want to go through and differentiate u plus v with respect to u, just like with xy coordinates, just like with rectangular coordinates. When you're differentiating with respect to one variable, you treat the other one as a constant. So the derivative of u plus v with respect to u is going to be 1. The derivative of 2 minus 3u with respect to u is going to be -3. And the derivative of 1 plus u minus v with respect to u is going to be 1. And then r differentiated with respect to v, the derivative of u plus v with respect to v is 1. The derivative of 2 minus 3u with respect to v is 0. The derivative of 1 plus u minus v with respect to v is -1. Okay, what does our definition have us do? We need to go through and find the length of the cross product. So let's do that next. You want to do RU cross RV. That is going to be I, J, K, 1, -3, 1, 1, 0, -1. So that equals I. And we're going to get 3 minus 0 minus J. And we're going to get -1 minus 1. That's -2 plus K. And we're going to get 0 minus -3. That's 3. Okay, and so that's our definition. And then so we've got then the length of RU cross RV is going to be the length of 3I plus 2J plus 3K. And to find the length, we do the square root of the components squared. So we get 9 plus 4 plus 9. So that equals the square root of 22. All right, and then we can move on to the next page. So then our integral. All right, so what is our definition here? So it's our integral this dA. So we want to take the result of this. The result of this was root 22. So we just want to pop that in. So we're going to have root 22 dA over d. And what did it say that d was? D is our restriction on u and v. U is from 0 to 2. V is from -1 to 1. So we can do this quite easily. Do 0 to 2, -1 to 1, root 22, and we'll do du dv. Okay, and so you could do this lots of different ways. I'm just going to take the root 22 out of here. And so -1 to 1, the antiderivative of this is u from 0 to 2 is going to end up being 2 minus 0. It's going to be 2. So we're going to get 2 root 22, -1 to 1 dv. So that's going to be 2 root 22 v from -1 to 1. Plug in 1, you get 1. Plug in -1, you get -1. Since you subtract, you do 1 minus -1. And so you're going to get 1 plus 1, which is another 2. So we're going to get 4 root 22 as our result. Okay, and so that's a quick example for going through and using our parametric surface definition. Let's try another one. Maybe it's a little bit more challenging. So we want to find the surface area. For part of the cone z equals the square root of x squared plus y squared between z equals 1 and z equals 2. All right, so you might go through and say, all right, I'm just going to use the old-fashioned surface area definition for rectangular coordinates. This is defined in terms of rectangular coordinates, and that's probably fine. I think actually if you do that, it's actually easier, but we're practicing using the parametric surface definition. So what we want to do is we want to go through and use parametric surface method to find this surface area. To do that, you're going to need to take this and translate it into parametric surface first. So we use our method for translating from rectangular to parametric surfaces. Since you've got x squared plus y squared here, we can go through and do x equals r cosine theta. We can do y equals r sine theta. We can do x squared plus y squared equals r squared. Right, and then we can go through and just use this. This tells us that z equals the square root of, instead of x squared plus y squared, we can use this to say that's r squared. So z is going to equal r. Okay, and now again, like we did earlier, I do want to caution you, change over to u and v here. This can be especially confusing when we're going through and we're integrating over r's and thetas, because you're going to want to think in terms of changing to polar coordinates, but we're not changing to polar coordinates. We're going through and using these polar coordinate definitions to define this, define our object. Once we've got it into u's and v's, the shift to polar coordinates has already happened, right? So don't go through and try and put an r d theta in there. That's not right. Okay, so what we want to do here is just use these definitions. We're going to have u cosine vi. Again, this is the easiest way to do it. If what I just said doesn't make any sense to you, then just do as I say, and that is don't use r's and thetas in your definition. Use u's and v's. And then we're going to get u sine vj. And then finally, we're going to get, right, so r is what we've called u, so then we're going to have uk. All right, so once we've got this, once we've got our definition here, oh, and then finally the last thing, z equals 1 to z equals 2. So we know that, what are we going to know? What are we going to say about, since z is equal to r, and we're using u for r, that means that u has to be between 1 and 2, right? Okay. So once we've got our surface, so that's the first step. When you're going through and using finding surface area using a rectangular coordinate definition, and you want to use the parametric surface area formula, you first have to change to parametric. And that's what we've done. This is parametric. The next thing, once you've changed it to parametric, is you're just following the definition here. What is our definition? We want to find RU, RV, cross product, length. All right, so let's go through and do that. Maybe try and fill this space in here. So we've got RU, differential with respect to u, that's going to be, we're going to get cosine vi plus sine vj plus k. And then rv, so we're going to have negative u sine vi plus u cosine vj plus, and then the derivative of u with respect to v is going to be 0. So the k term just drops out. No k term. And then ru cross rv is going to equal, we're going to have enough space here. Let's see if we can make this work. I, j, k. Then we're going to have cosine v sine v 1, negative u sine v, positive u cosine v 0. Then we're going to get I times I 0 minus u cos v minus j. And then we're going to have cos v times 0 minus negative u sine v. So we're going to get positive u sine v. And then plus k, we're going to get u, multiply these two, we're going to get u cos squared minus negative u sine squared. So this is going to be plus u sine squared. Oh, and we made it fit. All right, so that's RU cross RV. We can simplify that on the next page. RU cross RV is going to equal, wait, what was it again? So it's going to be negative U cos VI and then negative U sine VJ. And then finally, if you factor out the U here, this is sine squared plus cosine squared. So you're just going to get one. So it's just going to be UK. All right. And then next we want to go through and find the length of the cross product. This is the square root. We're going to get U squared cos squared V plus U squared sine squared V plus U squared. Right, and so you could factor out the U squared here and you'll get sine squared plus cosine squared. So that's going to be 1. This is going to be the square root of U squared plus U squared. So we're going to get 2U squared, which is square root 2U. And now constructing our integral, we have this thing here is what goes in our integral, and that is root 2U. Okay, and then we want to have dA and D. Okay. So looking at our object here, looking at our object here, we said that U needs to be between 1 and 2. We haven't put any restriction on V, right? Well, but V is, again, going back, V is kind of like theta. We just want that to go around 1 time. So we want V to go from 0 to 2 pi, and then U to go from 1 to 2. So hopefully that made sense. All right, so we're going to go through and do 0 to 2 pi, 1 to 2, square root 2 U du dv. Okay, don't do an r dr d theta. No, don't do that. That's not right. So the antiderivative of this is going to be root 2 U squared over 2. 1 to 2 dv. So we're going to have 0 to 2 pi. Plug in 2, you're going to get 4. Plug in 1, you're going to get 1/2. Oh, sorry, you're going to get 4 over. Well, maybe I should just write it instead of describing it. All right, let's do this. Pull out the root 2. Plug in 2, you get 4 over 2, which is 2. Plug in 1, you get 1/2. Like that. dv. All right, what's 2 minus 1/2? We got 4 halves minus 1/2. That's 3 halves. So we're going to have 3 root 2 over 2, integral 0 to 2 pi dv. That's going to be 2 pi. So we're going to get 3 root 2 over 2 times 2 pi. That could cancel that. And so we're going to get 3 root 2 pi. All right. And there you go. And that's a second example where we go through and use the parametric surface definition for surface area. And this one, you actually had to parameterize the surface first, and that's okay. All right, so this is one way to go through and handle these surface area problems is to, instead of using the surface area definition from rectangular, we can take our surface, parameterize it into a parametric surface. Then once it's in the parametric surface form written right here, we then can go through and apply our parametric surface area definition to it by the steps that we wrote. Okay, that's kind of cool. It just gives you an alternate way to go through and do things. And that's it. That's it for surface. That's it for parametric surfaces. Thank you for watching, and I will see you next time.